This is Zhenghang from HKUST. Our work is about GPU communication over multiple NICs. So the explosion of AI applications, especially the large language model, has created demand for high bandwidth GPU interconnect. Such requirement drives the interconnect advancements in mainly two directions. And the first one is the dedicated high-speed fabrics. For example, we now have NVLink and we have AMD Infinity Fabric. This type of dedicated fabrics connect multiple GPUs in a relatively small group with massive bandwidth so that it can collaboratively compute a large model in parallel. This type of bandwidth grows fast in recent years. Now it can reach nearly a terabyte per second. The second type of direction is to connect the GPUs together as a very large GPU cluster. This is handled by the general purpose RDMA network interface cards, or NICs. Those NICs are directly attached to each GPU in the network switches. And each NIC is responsible for its directly attached GPU for inter-server communication. But the inter-server bandwidth is not a solved problem. The single NIC bandwidth grows quite slowly in recent years. Now it has only 100 gigabytes per second. But we need much higher bandwidth than that, especially when we want to transmit a very large volume of the KV cache, which is produced when we serve a large language model inference task. Facing the high bandwidth demand, our intuition is to improve the inter-server bandwidth by multiplexing these NICs among GPU and merge those NICs as a super NIC for inter-server communication, so that the super NIC can transmit data for any GPU within this group. But before that, we must answer two questions. First, when can we multiply the NICs and accelerate inter-server communication? And second, with PCIe limitation, how can we leverage those dedicated fabrics to improve bandwidth over general NICs? So our observation is that we can leverage the idle NIC under traffic imbalance and relay the data efficiently through the dedicated GPU fabrics. The GPU group can be large now, such as the NVIDIA NVL72 system. We have 72 GPU connected through the NVLink. Such a large group can be deployed with multiple independent tasks. For instance, we can partition the GPU group to serve two independent models. Model A runs on one side of GPU and Model B runs on the other. And they use their attached NICs to transmit the KV cache for token generation. Because they serve different uncorrelated requests, their network traffic is also independent. It may happen a case that when a request arrives from Model A, the Model A's NIC becomes busy, and the Model B is idle. Their NIC is idle. So in this scenario, we can accelerate inter-server transmission by leveraging those idle NICs. Such traffic is transmitted by the GPU interconnect, allowing to bypass the PCIe limitation and benefit from the high-speed intra-server connection. In general, we can find other situations to multiply the idle NICs during the idleness. The first case is when the GPU have biased traffic volume. If communication workloads are not perfectly distributed among the NICs, some NIC will be busy while others will sit idle. And the second case is when the traffic transmitted over the suboptimal PCIe path. The traffic may pass through the CPU interconnect and will lead to suboptimal NIC throughput. And the third case is when GPU have delayed communication because the GPU are very they are different chips, and sometimes they have delayed communication pattern. And so some of the NICs will be idle for a while. All these cases will lead to suboptimal NIC utilization. And we can leverage such idleness to improve the inter-server communication bandwidth. Although we can do this case by case, like whenever I encounter such traffic imbalance, I modify the traffic scheduling to make them perfectly balanced. How can we do this automatically? Can arbitrary machine learning workloads to effectively leverage all the available NICs as a FuseLink for inter-server communication? So to build such a general system, our design is guided by these three key principles. The first is efficiency. We aim to efficiently leverage the idle NICs for inter-server communication so that they can manage them as independent resources without bottlenecks. The second is the ease of use. The entire system, we want it to be operate transparently to the application, integrating directly with the existing communication libraries like the NVIDIA NIC without requiring any code changes. Well, the final one is the fairness. The GPU do share the NICs, and we want them to use their direct NICs whenever they have communication tasks. And we want to leverage those idle NICs whenever they are truly idle, so that we can avoid such contention. So why is this difficult? The challenge is the fundamental incompatibility between these two types of network. That's the dedicated fabrics and the general RDMA NICs. The dedicated fabrics like NVLink, they cannot talk directly to the RDMA engine. Now, suppose if I have an idle NIC, and I wanted to utilize this idle NIC to send data through the NVLink and the PCIe. But a NIC RDMA engine can access the memory only of this directly attached GPU over the PCIe bus. But that NIC cannot access the GPU memory through the NVLink fabric because they are different protocols. And they are different communication domains. There is no hardware mechanism to effectively route RDMA traffic through the NIC across the PCIe bus and eventually on the NVLink. Also, as the network stack of the RDMA is implemented in hardware, there is no way that we can change the NIC or GPU network stack to merge those two different protocols. So to solve this problem, we began by investigating how GPU communication network stack and data path looks like. A typical data path is the source GPU write data to a registered network buffer, and then handled by the NICs and write to the remote buffer. To achieve application transparency, we want to keep the network buffer address unchanged, and then route the data to idle NICs through the dedicated fabrics. Well, a straightforward solution will be simply copy the data through the dedicated fabrics, and that GPU should have direct connection to the idle NIC, and then followed by the NIC transmission. But this will require extra copy on both sender side and receiver side, and will degrade the overall throughput. To avoid the extra copy, we can remap this buffer to another GPU using the virtualizing memory system. But this will require register this buffer again on the NIC because we have changed the virtual to physical mapping. This will cost up to 1 millisecond, which cannot be accepted in our system. So our key design is we can eliminate the extra copy or memory registration by decoupling the GPU address and network buffer. First, we can give another address that's mapped to the same physical address as a network buffer on the GPU side. That's an alias of the physical pages or physical memory. And we register another address instead of the network buffer itself. And we keep the register buffer unchanged and dynamically change the mapping of the network buffer on GPU side. So this is how it looks like. Upon GPU filling the network buffer, we dynamically decide the mappings of the GPU side address to the network side address. This allows flexible intra-server data routing because we can now dynamically change the mapping in runtime. A single GPU now can use multiple NICs by changing the mapping and use different register buffers. The remapping usually takes 100 microseconds, which is acceptable in our system. And this is how it looks like when we change the network mapping. First is mapped to GPU-X, and when it's write, the data is transmitted to GPU-X and then transmitted by its directly attached NICs. And we can change the mapping to the location B on GPU-Y so that it can change this usage of NIC from the upper one to the lower one. Finally, we divide the memory buffer into multiple slots and dynamically change each slot mapping to different GPU. So when GPU fills the network buffer, the traffic will be routed to relay GPUs through the dedicated fabrics with very high speed and finally sent through multiple NICs. So the network buffer address is not changed throughout this process. It's totally transparent to the application. Next, to achieve the load balance and avoid NIC contention, we implement a simple NIC load balancing monitor within each server. The monitor records the ongoing transmission task on the both sending and receiving direction. In this example, the GPU detects the direct NIC for inter-server communication. They attach log status as the part of the RDMA traffic and exchange such information so that they know which NIC is idle for multiplexing. When idle NIC exists, the sender will automatically forward part of its traffic through the idle NICs to keep all NICs busy. And when the GPU with direct connection, that's the lower one with the yellow arrow, and the NIC contention is detected and the NIC resource is preempted. So based on this design, FuseLink can be summarized as all these three essential components: the NIC idleness detection, the NVLink and the NIC transport, and the contention elimination. We choose the NVIDIA platform as our implementation, but other platforms like AMD, they also support such P2P access and remapping operation. So that is also applicable. Well, to test FuseLink, we set up servers with 8 GPU and 8-lane NVLink and 400G NICs. We manually set up the number of NICs that it can use to test the 2 inter-server GPU communication bandwidths. The results show that we can effectively get higher inter-server bandwidth by utilizing multiple NICs. And in this case, the intra-server connection acts as a dedicated switch so that we can use different NICs effectively. And we can see that when we use 6 and 8 NICs, the bandwidth seems to reach a limit because now we have fully leveraged the 8-lane NVLink bandwidth and reaches the maximum inter-server bandwidth. In our end-to-end evaluation, we test some of the most favoring case. We deploy 8 independent serving instances within each server, and we record the time it took for computation and also the KV carrier transmission. For 8 instance case, because all the GPUs are independent, they can leverage all the available NICs whenever they are idle. But if we place only 2 serving instances, We admit that it brings very incremental improvement because we deploy the model with tensor parallel as 4, so that every 4 GPU are highly synchronized, and we can have only very little chance for multi-NIC acceleration. FuseLink can also accelerate the imbalanced traffic in the machine learning task. We test 2 typical cases. The first one is the acceleration of the imbalanced all-to-all traffic in the mixed-trail expert parallel training. And also, we test the embedding transmission in the recommendation model when where the GPU have to transmit the embedding vectors independently from the embedding table. As a prototype system, we hope FuseLink can be further developed into a more general system, like the supporting of more GPUs. And we rely on standard RDMA verbs and GPU P2P access feature, which are widely supported in today's GPU products. And our current design tries to route chunks of data to different NICs instead of per packet load balancing, because the remapping may take a long time. So our current design stays on the per chunk load balance. So that could be all for this work's introduction. I'm happy to take all the questions.